All right, so to begin with, on this section, we're mainly going to be talking about inverse functions. And that's kind of a big deal in math. It's a big deal in calculus. And in order to understand what a one-to-one inverse function is, you have to understand what a one-to-one function is. So I'm just going to explain that. This is the way the textbook defines this, which is sometimes a little confusing the way this says. This says a function is one-to-one if any two different inputs to two different outputs. Wow, that didn't like export correctly or something, didn't it? Something got chopped off of there. Does it say something differently on your handout? Okay, well, let me read the thing that's the most important. Sometimes these things don't convert when they go into OneNote correctly. So this is kind of the way I look at it. You ask the question, does each element in the range have exactly one element in the domain? That's why I teach it anyway. There's different ways to write that definition of that anyway. So it's kind of like backwards of a function. Remember, in a function, we ask the question, does every element in the domain map to exactly one value in the range? Well, we do this backwards. So what we would do on this, we're going to look at these mapping diagrams and just see if they're one-to-one. So here's the question you ask. Does every y have exactly one x? Okay, so like Bobby, yeah, goes to Cindy. Peter goes to Jan. Greg goes to Marcia. Okay, so the answer to that question is yes, every y goes to exactly one x. We're doing that backwards. So that would be a one-to-one function, okay, like that. All right, that's the old television show, The Brady Bunch, in case you don't know. Nobody, you know, I knew somebody would know. Okay, very good. That's a one-to-one family. Everything's just perfect, you know, 3 boys, 3 girls and everything. Okay, let's look at this next one. And this is kind of the same way. This is, you look at an element in the range, and that goes to one place. Okay, that's good. Lucy goes to one place. And then Peggy goes to one place. That's the 3 stooges in the domain there. Okay, so that would be yes, and that would be a one-to-one function like that. So, but that's what you're always doing, is asking that basic question then. Okay. All right, how about the next one? Does every y have exactly one x? What's the answer to that question now? Oh, that's no, clearly. Okay, the owl is going to 3 different places, so that's no. So that would not be a one-to-one function. Okay, that's what you're looking at first of all. How about the next one? Does every thing in the range just have one thing in the domain? Yeah, okay. All right, now you got to be careful about this one. Okay, that definitely is true. But let me ask this question. Is this a function? Because we learned earlier what a function was, right? Do it backwards. Does every x have exactly one y? No, so it's not a function. Okay, and if it's not a function, then it can't be one-to-one. Okay, so it's just not a function is the thing. So if it's not a function, you know, worry about whether it's one-to-one. Okay, that's the idea. All right, any questions so far? Okay. All right, so just looking for every element in the range to map to one element in the domain. It's the opposite thought process you do for a function. Okay, this one kind of goes like this. You can also you can do this in your head, but I'm just going to kind of write this like this. The domain is 2, 3, and 5, and then the range on this is the 2 maps to a 6, the 3 maps to a 4, and the 5 maps to an 8, okay? So, does every y have exactly one x? Yes, okay, so that is a one-to-one function, okay? You don't have to write that mapping diagram down, but you can if it's helpful to you, okay? And I'll do basically the same thing on this next one. The domain, we have -3 and -2, and both of those things map to 4, so you can write that kind of like that. And then we have a -1 that maps to a 2, and then we have a 0 that maps to a 6, okay? So again, if you're going to determine if it's one-to-one, ask the question, does every y have exactly one x? Is that yes or no? That's no, okay? The problem is that number there, and I didn't have to put that 4 twice, okay? That is going to 2 different places. So if you do that, the 4 is mapping to 2 different x's like that. So that's not a one-to-one function, okay? So that's the idea. Okay, is everybody solid with what I mean by one-to-one so far? All right, that's the way I teach. It's a little easier, I think, to think of it that way than the definition we have in the book then. Okay, So next thing on this next page, we've already talked about the vertical line test. We haven't talked about the horizontal line test yet, and that's how you can look at a graph and determine if it's a one-to-one function or not. And I'll explain why that works. So basically, the horizontal line test just says if you do a horizontal line and it passes through one point everywhere on the curve, then it would be a one-to-one function, okay? So first of all, as we look at these, we're going to do two things. And you do this in your head. You don't have to really do anything in your paper. But if you did the vertical line test, does that pass the vertical line test? Yeah, so that's a function, okay? That's what that's saying, okay? And then the question is it one-to-one? What would happen if you did a horizontal line? Would that go through one point or more than one? It goes through two, okay? So that's not one-to-one. So that's what the horizontal line test does, is it determines whether or not you're going to be one-to-one or not. And here's kind of the reason for this. You don't have to write this down necessarily. I'm just pretending like I know this point is 4, 2, and I'm saying maybe this point is the point negative 3, 2. I'm just predicting that. Well, the idea is you have the same y with two different x's. So that's why it's not one-to-one, okay? That y has more than two x's to it, okay? All right? Okay, how about the next one? Is it a function? Yeah, okay, that passes the vertical line test, okay? You just kind of do that in your head, okay? How about one-to-one? Yeah, okay, it passes the horizontal line test, so if you take horizontal lines like that, those are only going to go through one point. So that's kind of what a one-to-one function will look like, is like that. So it's got to pass both the vertical and the horizontal line test. That's the idea, okay? All right. How about the next one? Is this a function? Yeah, okay, it passes the vertical line test, so we know that's good. Okay. So now it's a function. That's a line. How about the horizontal line test? Would it pass or fail? It'd fail pretty badly, wouldn't it? I mean, the only thing you can do is just draw a horizontal line through the line that's already horizontal, and it's going to go through an infinite number of points, right? Okay, so that can't be a one-to-one function. The idea with that is the y value is always the same, and that one y value will have an infinite number of x's. So that's the idea, okay? All right, and the last one, is the last one a function? No. Okay, is it one-to-one? Well, it's not a function anyway. It fails both tests, so that can't be a function, nor can it be one-to-one. Okay, so that's what the horizontal line test does, is it lets you visually see whether something is a special kind of function that we call one-to-one. Okay? All right, any questions so far? Okay, generally that goes pretty smooth for students. That's not usually a very big deal. Let me have you draw a little diagram on these statements. I want to go through and explain what this is. And it's logical if you kind of look at a graph on this. This is saying if a function's increasing on an interval, then it has to be a one-to-one function. So what I'm going to have you do on this, let's just put like A there and B there. That's just going to be some interval from A to B. And I'm going to make a function that's always increasing. There's all kinds of ways to do this, but I could do something kind of like that. That function is increasing from A to B, right? Would that be one-to-one? Yeah, how come? Passes the horizontal line test. Okay, it has to. Okay, so what you're going to find if you have an interval where you're always increasing, then it has to, it's forced basically to pass the horizontal line test, therefore it's one-to-one. The next example is just the opposite of that. If you had an interval from A to B and you made a function decreasing the whole time, then it would do something like this. Let's just say we have a function kind of doing something like that. Is that one-to-one? Yep, absolutely. Okay, so if you find a point, a place on the graph where you're always increasing or a place where you're always decreasing, it's going to be one-to-one in that interval. That's what that means. Does that make sense to everybody? Okay? All right, so that's kind of gets you through the part of what a one-to-one function is, and that's real important because it's tied to what an inverse is. So we're going to work a lot today on what inverse functions are then. Okay? Okay, so if we go to the next page, this is kind of where we get into the idea of what an inverse function is. And the idea is, first of all, you do an inverse only of a one-to-one function, okay? And this says you can only invert a one-to-one function. So if the function's not one-to-one, then it's not going to have an inverse, okay? Now, let me explain this, the y part, kind of like this. Let's just draw this mapping diagram right here. I'm going to draw something that's not one-to-one, okay? So let's say that we have something like 1, 2, 3, 4, and let's say that all we have in the range is like 2 and 5. Let's say that maps there, that maps there. Let's say the 3 and 4 map to 5. Now that's not one-to-one. The reason it's not one-to-one is because this y has 3 different x's. Okay, so that's not one-to-one. Even if you plotted those points, that would fail the horizontal line test. So that's not one-to-one. Well, what you're going to do is when you do an inverse, you just interchange the variables. So everything goes backwards. So what would happen is, if you made this into an inverse, then the 2 and 5 would become your domain, and then the 1, 2, 3, 4 would become the range. Okay, and what would happen is the 2 would map to 1, the 5 would map to 2, 3, and 4. Okay, so what you're doing on an inverse is you're flipping everything backwards. Well, is this thing right here, this thing that I just drew, is that a function or not a function? That's not a function, right? And it's because this 1x, 5, maps to 3y's. So what happens is it has to be one-to-one. Now, you don't have to write this down, but I'll show you another real simple example. Okay, this would be an example of a one-to-one function. Okay, every y has 1x. If I change everything backwards, then it would go like this, and then that would be a function. Okay, so what happens if something's not one-to-one and you invert it, it won't be a function. Does that make any sense to you? Okay, the idea, just kind of look at this example right here. When you changed everything backwards, it's not a function because the 5 went to 3 places. So one-to-one, it's okay. All right. Okay, so first of all, what we're going to do is we're going to learn how to find inverses. So this is real simple. This is a function. Every x has exactly one y. So when we do the inverse, you do this symbolism. You say f negative 1, and that's not an exponent. That's just the symbolism for an inverse. And all you do is just change everything backwards. So it's very simple. All you do is just take each point and write everything totally backwards. So that point 110 becomes 10.1, and then you have 22, then you have 33, and so forth like that. So that's all an inverse is you're just changing everything backwards as long as it's one-to-one. Okay, and that's the idea. Okay, now what we talked about in the last class is we talked about composition of functions. So what I want to go over on this a little bit is this, and we'll do some examples to illustrate this. So if f of x is a one-to-one function and then you have its inverse, then what's going to happen is if you do the composition of functions, that's what we learned last class, then it should be x. So that's what's special about an inverse, is when you compose the two functions, the value of that will be x both ways. Okay, it's got to work both ways when it does that. The other thing we're going to talk about as we go through this is if the domain of the function turns into the range of the inverse, and then the range of the function turns into the domain of the inverse. Now, why that is because you're switching variables. So the domain changes to the range, and the range changes to the domain. Everything gets backwards, so that's why that works the way it does. Okay? All right, so to illustrate what happens on the composition of functions, we're going to do a couple examples. This is a good starting example down at the bottom of the page here, because these are 2 lines, so we're going to do this then. Okay? All right, so let's see. What I want to do first of all on this, there's a couple of things that I want to do before we even get into the graphing. I want to just focus on having you do this. Okay, so you want to write this on your paper. We're going to do f composed of g of x, and then we're going to do I'm going to probably have you guys do this backwards. I want to take you through how to do it one way, and then I'll have you do the other way and see what you get. Okay, so this is what we talked about last time. If you do a composition of functions, you always want to start by writing the first function down. The first function is 3 minus 2x. But instead of putting an x, put like a big grouping symbol, like a bracket or something. Okay, now what's going to happen is, when you do a composition, the other function just plugs into it. So the g of x is going to plug into that bracket like this, so you would have negative 1/2 times x minus 3 like that. All right, so you're just taking the first function and plugging the other function into it. Does that make sense? That's what we mean by composition. Now we're going to work this out and see what happens. So that would be a 3. See, when you multiply like the negative 2 times the negative 1/2, the 2's cross out and that gives you a positive number. So right there, that's just positive 1 times x minus 3. Okay, do a distributive property, see what happens. So this is going to be 3 plus x minus 3. So what's the result? X, okay? And that's what we're looking for in order for something to be an inverse, is that should happen, is that composition gives you x, okay? Now, let's do this backwards. I want you guys to go ahead and do this backwards and just see if you are following what I'm doing on the composition. Write down the g, but then plug the other function in for x. Work it out and see if you get x. So go ahead and take a minute to do that and see if you can do that okay. Then what we'll do is we'll look at the graph and we'll kind of visually look at what happens on these graphs. If you do it right, you should get x. Okay, if you get everything kind of put together and do the algebraic simplification correct on this, you should get x. Okay, if you're having trouble setting it up, I've got it set up here on the screen here. So again, I just wrote down negative 1/2, but replaced the x with the other function. Okay, like that. So it's negative 1/2 times 3 minus 2x minus 3. Okay, and what's going to happen is, notice the 3's are going to cross out. Okay, then what you'd end up having is you would have negative 1/2 times negative 2x. Okay, that's going to be x. If you multiply that straight across, you get 2x over 2. So that's equal to x. So what happens on this is, when we did the composition both ways, we ended up getting x. That proves that those two functions are inverses of each other. And then we'll talk about what that is. All right, does that make sense, what I'm doing on the composition? Okay. Sometimes students, if they've never done that before, have a little trouble understanding how to plug it in. It's just one function goes into the x of the other function. Okay? All right? Now what we're going to do is we're going to graph, and I'm going to do a table of values on this. So this table that I gave you down here, we have f of x equals 3 minus 2x. I'm just going to pick a couple of points on this and then show you what happens on this. So let's start with x equals 0. We're just going to keep it simple on this problem. So if I plugged 0 in for x, I would have 3 minus 2 times 0. That's 3 minus 0, so that's 3. Okay, these are lines, so I just need to get 2 points. So I'm not going to do slope-intercept on this. Let's also pick, like, let's say 1. Okay, do that. No, actually, I'm going to change my mind. Let's do 2. Okay, so let's just do x equals 2. All right, so then we would do 3 minus 2 times 2. That's 3 minus 4, so that's negative 1. Okay, and then I'll show you kind of what I'm going to do next here, because I want to show you something on these table of values. I'm just kind of picking x values that are good illustrations of this. Okay, so what you want to do is you want to plot those 2 points. Okay, on your graph, you've got 0, 3, and then you got 2, negative 1, And then that's a line, so you just connect the dots, put your double arrow, and that takes care of that. Okay? So we'll end up having that line, and what I'm going to show you is kind of how these things have a symmetry to them. So the next thing we're going to do is let's do the other function is y equals negative 1/2 of 2x minus 3. Now I'm going to do something on purpose. What I'm going to have you do on this is we're going to do this backwards. So in this table we're going to do 3 and negative 1 as our x values. And we're going to see if they produce the 0 and 2. They should. We just proved it's an inverse. So I'm going to do this at the side of the paper. I've just got y equals negative 1/2. I'm going to plug in the 3. So that's 3 minus 3. So that's negative 1/2 times 0. So that's 0. That's what we expected to get. We expected the 0, 3 to change in a 3 to a 3, 0. Because we know it's an inverse. We already proved it. Okay, then we're going to plug the negative 1 in. So you have negative 1/2 times negative 1 minus 3 like that. And then we should get 2 if we do the arithmetic right. So that's negative 1/2 times negative 4. That's 4 over 2, so that's 2. Okay, everybody with me on what I'm doing there? Okay, I just picked 2 points. It doesn't matter what points I picked. That would have happened is you would see the points going backwards. So you want to plot these points. So we want to plot 3, 0, and then negative 1, 2, and then connect the dots like that, and then that'll give you the 2 lines like that. And then I'll show you how this is symmetrical. Anytime you have an inverse, it's always symmetrical about the line y equals x. So we're also going to graph that because I want you to visually write down a couple of things on the graph then. So if you graph y equals x, again, I'm just going to pick 2 numbers. It doesn't matter what I choose. I'm going to choose negative 4 and 4. That's just whatever. Well, if it's y equals x just means x and y are the same. So if you plot those 2 points, then we're going to get what this graph where it's symmetrical about y equals x. So if I plot the point negative 4, and the point 4, 4, and then you want to just kind of take a dashed line. That'll go through the origin, 0, 0, and then that would be y equals x. Okay? So what you're going to always see on an inverse is they're always going to have this kind of symmetry to it. So a couple of things that I want you to kind of make a note of on your graph, like this is a point 0, 3, so I want you to notice that the point 3, 0 is on the other graph. Okay, this is a point negative 1, 2, so you want to notice that 2, negative 1 is on there, like that. Okay, that's what an inverse looks like, and the graphs are always going to be symmetrical about that 45-degree angle line y equals x. That's the idea. Okay, so that's first example to kind of illustrate what we mean by an inverse. Does that make sense? Okay to everybody? Okay, all right, so basically the points go backwards. When you do the compositions both ways, it'll turn out to be x, and that's what it ends up being symmetrical about, is about that line. Okay, any questions about what we did? Are we okay? Are we awake? Okay, all right, that's good. Okay, now sometimes the algebra on these will get a little bit more complicated. So this one we're going to do a graph on the TI after we do this, but this one is going to have some algebra things, but we've done enough of this already. So what I'm going to do is I'm going to do f composed of g of x. I just kind of divide my paper into 2 parts. Then I'm going to maybe have you all take a few minutes to see if you can do it the other way. Okay, so what we're going to do is if we're going to show these are inverses, what's the result supposed to be again? When I compose, what is it? X, right? Okay, that's what we're going to try to show. Okay, so here's what you do on this. If you're going to do it this way, you start with f of x and use kind of a framework on this. Put something minus 5. I like to use brackets or parentheses. The denominator is 2 times something plus 3. Okay, so I'm just writing that down. And what's going to go into my brackets? the other function, right? Okay, so you want to go ahead and plug that other function into that. Okay, so we want to put in the 3x plus 5 over 1 minus 2x. Okay, like that. Okay, now we've done this before. We've seen these things that are complex fractions, so we got to deal with this. Okay, sometimes students don't have a very good background for this kind of stuff. So what are you going to try to do with that expression to make it simpler? It's got fractions within fractions, so what do you do generally? What have we been doing? We want them to go away, right? So how do you make that go away? Multiply by it, good. Okay, you got to do the top and bottom by that. You have to. Okay. So what we'll do is you just need to show on your paper that you're going to multiply the top by 1 minus 2x, and then you multiply the bottom by 1 minus 2x. Okay, kind of a grouping symbol, whatever that grouping symbol is. You can use braces or parentheses or whatever. Okay, now, what we'll do on this, I'm going to go ahead and write this step. You can learn to do this in your head, though. I've taught you how to do that. So you're doing a distributive property. So you would have 3x plus 5 over 1 minus 2x times 1 minus 2x. And, of course, that's going to cancel that out. That's why we do that. And then we're going to distribute the minus 5 through the 1 minus 2x like that. Okay, now we're going to do exactly the same thing in the bottom. You can bypass this step if you can process it in your head, okay? Just be careful if you do. Then the bottom we're going to distribute, so you're going to have 2 times 3x plus 5 over 1 minus 2x. And then that gets multiplied by 1 minus 2x. And then plus 3. And then that gets distributed by 1 minus 2x like that then. Okay, so the reason I'm doing that is because that will wipe out the fractions. So what's going to happen is that's going to cross out there, that's going to cross out there. So we don't have a complex fraction anymore, and then from here, it's just a matter of simplifying what we're left with. So what we're left with on this is we have a 3x plus 5. You can go ahead and do a distributive property here, so that's minus 5 plus 10x, okay, like that. Okay, same thing kind of happens in the bottom. You've got a 2 left over times 3x plus 5. You can actually go ahead and distribute. I'm just going to do that. There's no sense in writing another step. So you'll do the 2, that'll give 6x plus 10. And that takes care of that. And then this will be plus 3 minus 6x. Okay, so that's the idea with that. And you want to get really solid with complex fractions going into calculus because they show up a lot and you want to know how to just get rid of the fractions. Okay, well, you're going to see a bunch of things canceling out, I think, on here. So what's going to happen is the 5's cross out and the 6x's cross out. So it looks like the numerator is 13x, the denominator is 13. The 13's cross out, so that is x. Okay, so that by itself doesn't prove it's an inverse because you got to do it the other way. Okay, do you guys follow the algebra okay? Anything I need to clarify there? Okay, all right. Well, let's go ahead and set this next one up, and then I'll let you guys see if you can finish it. Now, what you want to do with this one, it's almost the same thing I just did, except you're going to do it backwards. You start by writing down the g of x. So g of x is 3 times something plus 5. All over, and then the bottom is 1 minus 2 times something. Okay, go ahead and take it from there. Let's see what you can do. It's the same principle. You'll have a complex fraction that you'll have to go through and get rid of. Okay, so take it from there and let's see how many people can get this okay. And you'll get x. I mean, if you're not getting x, you're messing up in there somewhere. So take it from there, get rid of your fraction, and see if you don't get an x on that. You can skip a couple of steps on this if you're confident in what you're doing. I don't mind that. Are we getting X yet? Okay, some of you getting it? Okay. I'm just working it out while you are, and then we'll look at this in just a minute and see if we have any trouble. But as long as you can get rid of that fraction, okay, don't make any sign issues or anything like that. What's ultimately going to happen, it looks like, is going to look a lot like the problem we just did. You're going to end up with a 13x on top, a 13 on the bottom, so you got x. Okay? Now, see, one thing you can do on this, you can process in your head. I do this all the time when I'm doing the problem. That's going to cross out, so that's going to leave you. You can jump all the way down here. That's 3 times x minus 5, and then plus 5 times that. So you can bypass that step if you're comfortable doing that. Then 2x plus 3 times 1 gives this. That crosses out. That gives you minus 2 times x minus 5. So once you get down to that point, it's pretty straightforward, and you'll end up just getting the 13s to cancel out and getting an x. Okay, so what that is that means that is an inverse. Does that make sense to everybody, what we've done? Okay, you'll see some things with complex fractions. Now, what I want you to do next is I'm going to have you put these two functions in your calculator. Okay, I'm not going to have you draw a graph on your notes or anything, but please do this. So what you want to do is just go to y1, and you want to put in the first function. So the first function is x minus 5 divided by and then 2x plus 3. Be sure to use parentheses when you're doing a rational function. Okay, we'll do that. And then go to y2 and put the second function in, which is 3x plus 5 divided by 1 minus 2x. And you can just do that in Zoom 6, a standard window if you want to, because all I want you to see is this. The other thing I want you to do is in y3 just put y equals x, okay, because that'll kind of determine the symmetry on that like that. So you want to get those 3 functions in, and once you do that, you can just go Zoom 6. All I want to do is just display this for you. I must have put something in wrong. Anytime it does that, go to the Go To button and it'll tell you somehow I did something wrong on there. What in the world? Oh, I left off a parentheses what I did there. Okay, now I think I'm good. Okay, so I'll try it now. Okay, so this is, if you put it in correctly, that's what you should get. All right, so really what's happening on this is the blue graph is, I think, the first one. The red graph is the second one. Does that look symmetrical to you? Yeah, so I mean, you can visually a lot of times tell if everything looks correct. And what you're going to find is the points are just backwards on those two graphs. If you looked at your table of values, you would see that everything's kind of reversed on those. So visually, you can go through and see that okay, any time that you do that then, all right? All right, is there any problem with anything that we did on that problem? Does that make sense to everybody okay? Okay, all right. And check them graphically if you ever need to. You can do that. So what I've done now is I've shown you how to tell if two functions are inverses or not. You have to do the composition. The graph doesn't prove anything. The composition does. Okay, if you get x composing it both ways, you will. So the next thing I want to do is show you actually how to find an inverse. and then we'll do that and look at the domain and range. So the first thing is you have to be given a one-to-one function. Now, when you start doing your MyMathLab homework, most of the time it's going to say, given the one-to-one function, find the inverse. So that's taken care of for you. There's a few examples where you're going to have to make it into a one-to-one, and I'll do one of those as we're going through this today. So this is a one-to-one function. What we're going to do is we're going to find its inverse. Okay, so this is what you want to do. The first thing you want to do is just write down the function. It's good to write it as y equals 1 minus 3x. Okay, so that's step one, just write it down. And then step two is just switch the variables. So this is the y becomes x, the x becomes y. Okay, because that's what an inverse is anyway, you just switch the variables. Now the next thing you're going to do is you're going to solve this equation for y, which is real simple in this example. You can just move the 1 to the other side, so I get x minus 1 equals negative 3y. You could do this the other way too if you wanted to. Then I can divide by negative 3. Okay, so what you would end up getting is this is y equals, and you can write this one of two ways. I would probably write this like negative 1/3 times x minus 1, okay? And what you do is you want to usually write this answer just like this. You just write it as f inverse of x equals negative 1/3 times x minus 1, okay? And that would be fine. Now you could get an alternative, an equivalent answer if you did the same thing on the other side. Now you don't have to write this down, but I'm just going to show this to you because you'll get into this in your homework. So if I wanted to rearrange it this way, I would get 3y equals 1 minus x, like that. And then if I divide by 3, I would end up getting y equals 1/3, 1 minus x. And I think it's pretty important to see the difference in those two answers. Okay, they're the same answer. And we've talked about this before. Remember, if you flip the order you subtract, what does that do? It introduces a negative. So if you take this thing right here and flip that, it would be 1/3 x minus 1, but it would introduce that negative. So they're the same answer, okay? Generally, like MyMathLab's usually programmed to take more than one answer. Theoretically, that's the way it's supposed to be anyway, okay? So either one would be okay. All right, so what we're going to do next is we're going to do the domain and the range of the function. So basically, you would want to know 1 minus 3x. What kind of function is 1 minus 3x? What do you call that function? It's linear, right? So what's the domain of any linear function? All real numbers, right, okay? So what we'll say on this, I'm going to do set builder notation on this. We're just going to say set of x, and we'll just say x is some real number, okay, like that. So what you're learning how to do on this then is, it kind of goes like this. Basically, this will turn into the range of the inverse. Since you switch variables, the domain of the function will be exactly the same as the range of the inverse. The difference in the way you write this, though, a range is a y value, so you'd say set of y, and you would say y is a real number. So it goes like that, okay? And that would be the idea. All right, now what I'm going to do on this is we're going to go ahead and do this. I'm going to have you go ahead and graph this original function. So that original function is y equals negative 3x plus 1. Now that's one that you can count out the slope and y-intercept and do without your calculator. You could use your calculator if you wanted to. So I'm just going to do this without the calculator. So I'd have a y-intercept of 1. The slope is negative 3 over 1. So that would mean that you go down 3 and to the right 1 like that. Okay, and I'm going to show you kind of a quick way to get the other graph without having to do much of anything. So this point right here, you want to label that point as 0, 1, and you want to label that point as 1, negative 2. Okay, so that would be the graph of f of x. Okay, we'll go like that. Well, what could you do with those 2 points, 0, 1, and 1, negative 2, to do the inverse anyway? Just flip them. Just change them around. So let's just do that. Just plot the point 1, 0, because that's going to change around. Plot the point negative 2, 1. Okay, and then that second line is going to go like that, and then that's going to have that symmetry like that. And again, when you plot y equals x just goes through a 45-degree angle. So it actually just goes through all of these points right there where x and y are the same. So that's going to have the type of symmetry that you would expect it to have. Okay, and that's the idea. Okay, so in my diagram here, the function that we drew was the blue one. What's the range of this function? That's all real numbers, right? The range of that is all real numbers. So when you do the domain and range, it's going to go like this. Okay, so for the function, the range is set of y such that y is a real number. And what that's going to do then is that's going to be the same as the domain of the inverse. So the domain of the inverse is all real numbers also. All right, so what this last thing is saying is, and there's times when it's kind of hard to figure out the domain and range of the inverse, but if you can figure out domain and range of the function, then you flip them and then you've got domain and range of your inverse. Does that make sense? Since we're switching variables, that's why the domain and range connect the way they do. Yes?
Is it still okay for set order notation to write like set of x EIR?
To have what again?
Like to do the set of x EIR instead of writing as real.
Yeah, that's fine. You're saying, I think, the symbolism.
Yeah.
Yeah, that's fine. You could do the shortcut. You could say y and then that real number thing. Okay. Yeah, that's fine. Okay. You can do interval notation too. Negative infinity to infinity is what it would be on all those. Okay. Okay. Any questions about what we did? Okay, and what's going to happen on when you find an inverse? Sometimes it'll be pretty simple. This one's not too hard to do. Sometimes the algebra is a little bit more complex. Okay, so let's see. I'm going to do a couple more of these. And what happens on this one is, this happens sometimes, not very often. So again, what I've done is I've given you that it's a one-to-one function. So you don't have to worry about that, but you can only do an inverse of a one-to-one function. Okay, so what we're going to do is you start this way. You just write down the function y equals 2 over x. Okay, then you flip the variables. Okay, so that's going to be x equals 2 over y. Then you solve for y. Okay, so it's always the same what you do. And when you solve this for y, there's several ways to do this. You could just cross multiply if you wanted to. So you would have y times x equals 2 times 1, so you would have yx equals 2, and then you could divide both sides by x. So what you would end up having is you would get y equals 2 over x. Okay, so the original function was that. The inverse is the same. That's kind of weird, but it can happen. All right, so what you would end up having is the answer to the problem would be f inverse of x is equal to 2 over x. Okay, so again, all I did on that is just kind of the process is always the same. Switch the variables, solve for y. Okay, does that make sense? Okay, now let's put this in the calculator. I just want to show you something on the calculator on this. And actually what I want you to do is just do this. We're only going to put one thing in. Since the answer was the same, you can still leave that y equals x in. So just put in y1, just put 2 over x, and then graph that in the standard window. So just graph that, and then I want to see if you see why the inverse is itself anyway. Okay. Well, if you graph that, does that automatically look symmetrical? It is. It's automatically symmetrical to begin with. So that's the reason why that inverse is itself. And what you would find on this, on your table of values, this is just something that's kind of worth looking at. If you look at the table of values on this, you'll generally find that you'll see how things are backwards on here. Let me see if I can find something like you have. Yeah, here's a good example. Negative 2, 1, like that, changed into, let's see, negative 1, negative 2. Hold on, that's not right. That's not what I want to look at. I want to look at this. There's a real simple symmetry to this like this. So you have this point 1, 2. Oh, hold on. No wonder this is not showing up, okay? I was thinking there was another graph there. So just look at how this is. 1, 2, 2, 1. Negative 2, negative 1, negative 1, negative 2. So it's already there. The symmetry is built within the function. That's the idea, okay? All right. So now what we're going to do is we're going to do the domain and range, and we're going to start just by doing these two things right here, okay? So look at the original function. So what is the domain of 2 over x in your head? You should do that in your head.
X can't be 0.
X can't be 0, right. Okay, so what we'll say on the domain is we'll just say set of x such that x is not equal to 0. Okay, or you could do interval notation also. I'm just going to do set builder, okay? If you look at the range, now a lot of times the range, you just got to look at the graph. So if you look at the graph, is there anything that y can't be? Yeah, it can't be 0 because you have a horizontal asymptote, right? So you're never going to touch the x-axis, so that's good. What you would have is the range of the function would be set of y, and y is not equal to 0 like that. Okay? So see, there's no guesswork in the... Once you get that figured out, then the answer to the inverse is automatic. So the domain of the function becomes the range of the inverse. And the only difference is put y not equal to 0. And again, the answer to the range of the function turns out to be the same as the answer to the domain of the inverse. Like that, okay? So that's how you do that. If you figure out domain and range of the original function, then it's easy to figure out what they are in the inverse. Okay, does that make sense? Everybody with me there? Okay. All right. Let's go ahead and finish this up. They're going to do one more problem, and then the last page is just some kind of simple things to wrap this up. Let's go ahead and get this done before we take a break. So this one, what I want to show you is... and you should already know what the graph of this looks like. I mean, what does x squared plus 9 look like on the graph? That's a parabola, right? And what does the plus 9 do? Everything goes up 9, okay? So I'm not even going to bother doing this. Well, I am going to put it on the calculator because I want to see something. I want to show you something on this, okay? And you don't have to do this. You can just kind of watch what I'm doing up here. So I'm going to put in y1. I'm going to change my window a little bit too, so I'm going to do x squared plus 9, and I need to maybe make that window go a little bit bigger. I'm going to do something like, I'm just going to say like negative 5 to 5, and then I'm going to expand the y's a little bit and go like maybe negative 20 to 20, like this. And you can put this in if you want to, but you don't have to. So that's just kind of the window I'm going to put in. And when I graph this, what I want to show you is something about the graph that's kind of important when you do this inverse. Okay, so the question on this becomes, usually, is when you look at this, is this a one-to-one function? No, okay, that fails the horizontal line test, so this is not one-to-one. And what would happen is if you change the points, the inverse wouldn't be a function anymore. So what you have to do is you have to determine a way to make it one-to-one. Okay, we can redefine this function so it's one-to-one. So let me see if you know what I'm talking about by that. What's making it not one-to-one, of course, is it's failing the horizontal line test. So what if we just ignored that right there? Now is it one-to-one? Yeah, from 0 to infinity, it's one-to-one. Okay, so we have to define it some way. So what we're going to do is we're just going to ignore this. And if you're going to find the inverse, you have to do this. So what we're going to say is it's one-to-one on the interval. And we'll just say when x is greater than or equal to 0. So we're only going to consider the inverse when x is greater than 0. Okay, because it's got to be one-to-one. You'll do this sometimes. Most of the time on your homework, you're going to be given one-to-one functions. But if you aren't, you have to redefine it so it is. Okay, so that's why I'm doing that. That's the logical way to define that. So when we do the inverse, we'll do exactly what we've been doing. We just have y equals x squared plus 9. You're going to switch the variables and solve for y. Okay, so you'll have x equals y to the second plus 9. Now just go ahead and solve that for y. So if you do that, you would have x minus 9 equals y squared. Okay, you do a square root of both sides. And remember, you have technically a plus minus anytime you do a square root of both sides. So you'd have y equals. However, you only want to use the positive one. Okay? Because what's going to happen is if you graphed this square root, it wouldn't be a function. It would look like this. It'd be kind of a parabola open around the x-axis. So you only want to use the positive one. So what we'll say for our result is f inverse of x is equal to positive square root of x minus 9 like that. Okay, so that is our inverse like that. Okay. Now what we're going to do with this then is we're just going to figure out the domain and range when we do this. Okay, so remember, you're used to saying the domain of x squared plus 9 is all real numbers. Not anymore. The domain is 0 to infinity because we had to change the domain so it's 1 to 1. So what I'm going to write on this is, I'm just going to do set builder notation. The domain of the function is set of x where x is greater than or equal to 0. Okay, we know that for a fact then. Okay, all right, if you were to go through and graph this, and you can always look at your graphing calculator. So if you were going to put in this, well, let's look at what the range is. This thing has switched up 9. So what's the range of that parabola? Where to where? 9 to infinity, right. Okay, so the range is the set of y such that y is greater than or equal to 9. That's equal to 9. I mean, that's a definite point on the graph then. Okay, so we defined the domain so it's positive. So it would be 1 to 1, and we figure the range out. Okay, well, now this is easy. How do you find the range of the inverse? What have I been doing? I flip them. Okay, so the answer to the domain of the function changes into the range of the inverse. The only difference is you use y. So the answer here would be set of y greater than or equal to 0. And then the answer here, the range of the function was y greater than 9, so the domain of the inverse is x, set of x, where x is greater than or equal to 9. Okay? Now let me see if this makes any sense to you, because we've learned all this stuff about functions. That's a square root, right? Doing the swoosh, what does that minus 9 do to that square root? Right, 9. Okay, does that make sense? That the domain is 9 and bigger? It's because of that. Okay, that's how that function got transformed. So that's the idea. Okay, so that you will have to do maybe 1 or 2 of these where you have to define the domain. This is a pretty good basic example. Okay, any questions? Okay. All right, let's do this last page. This is just kind of wrapping up what we did. Everything on here is real simple. So what you're doing on this one is, and I think your graphs probably came out a lot better than mine did. So what you want to do on this is a function, and it's a one-to-one function. This thing right here passes the horizontal line test. So all you're going to do the inverse is all the points go backwards. So you'd have 4, 1, 2, 0, 1, negative 2. Was there another point on my handout?
There was a negative 4, negative 2.
You had a point over here like negative 4, negative 2?
Yeah.
Okay. So what you want to do is change that backwards and then just plot those points. Okay. So you should have the full graph on here. So sometimes I need to change Word files to PDF so they won't come out right. So again, you just plot the point 4, 1. Okay, so that would give that point. Then you plot the point 2, 0. And then 1, negative 2. And then negative 2, negative 4. So your inverse would do something kind of like that. And then it would be symmetric about that line. So all you're doing is flipping points. That gives the inverse, okay? So if you have a given graph, that's how you draw its graph, okay? All right, the next one, just the same thing. Just find maybe, all you got to do is find like maybe 2 or 3 good points. So that point right there is the point, looks like to be 0, negative 4. This point right here looks to be 2, 0. So all you need to do is just change those. So that point is going to become 0, 2. This point is going to become negative 4, 0. That's probably good enough. You just kind of sketch the shape once you get that. So that vertex, that lower point, that minimum, will now go to negative 4, 0. And then the other point goes to 0, 2. So your graph would look like that. Okay? And you can tell it's symmetric about that line y equals x. That's the idea. So that's a real simple thing to do. Right? Okay? Last thing is just language. Okay, what this is saying, this statement right here basically tells you that if x is 4, y is 3. Okay? So this tells you that on the inverse, if you had x is 3, what would y have to be? It'd have to be 4. Okay, that's just testing your language, that you know the language of that. That's all that is. This one, this statement says that you have a point negative 3, 5. The inverse is saying you have 5, negative 3. So its answer is negative 3. Okay, so if you're given a point on a function, then again, everything goes backwards on the inverse. Okay, that's kind of, that last page is kind of a summary of the basic idea that we did. Okay, most challenging things for students to do with this is sometimes the algebra gets a little messy on the inverse, but not too bad. Won't be anything you can't handle. Okay, anything that we haven't done yet. Okay, so let's go ahead and take a break here for 5 minutes, and then we'll come back and we'll do 4-3. I've got a few papers that I need to get back. So I got your test finally. I apologize for the delay. You did a good job. It just took me a while. I had that done, and I had it scanned. I'll just give you the original copy. It's just as easy. Micah, Bella, Angel, is that one? Okay.
We're gonna get to.
Tim, Freimeyer. Micah, Bella, that was you? Is that you? Micah? Danielle? Angel Galvan, that's you. And Ben Lee. Robert, that's Jasmine. Cassandra. Timothy. Cindy. Let's see, Muhammad. Well, that's good. You did a good job on that. Next time you scan something, try to be a little bit, but do a PDF. I was managing that okay. It was a little hard to read. Okay. Right. Try that cam scanner. There's a free app for a phone called cam scanner. It works great. Okay. Just takes pictures of your pages and it converts it to these PDF. Bryce Porter. Let's see, Alex Despot, Abrian Castaneda, Jabor, Cindy Dolan. Okay, that's all right. What's your name back there?
Micah.
What is it?
Micah.
I'm not sure if there, you can come up here and see if there's any papers. I'm not sure if I have any papers for you or not.